Hello guys, welcome back once more to my channel. So in the last video we did some vector algebra identities. Now in this video let's do some vector calculus identities, and most of them involve differential operators. So if you haven't watched that video yet, please do so. Let's get started. First identity we shall concern ourselves with is the Laplacian of product of two scalar fields. So Laplacian is the divergence of the gradient of both of them. Now we can use a subscript summation convention here to have divergence of writing the gradient as this differential operator fg ei hat. We can do the same with this guy, but before that we need to use the product rule of differentiation for a product of functions f times g. So we get the dot product of g times partial f with respect to xi plus f partial g with respect to xi ei hat. And then this del is nothing but e sub j hat partial with respect to x sub j dotted with, well, g. I'm just copying this guy. So what I'm gonna have is I'm gonna have a Kronecker delta ij because of this dot product. So we can change the j to an I after applying the Kronecker delta. So we have partial with respect to xi acting on this entire thing, g partial f with respect to xi plus f partial g with respect to xi. And again we can expand this out, use a product rule again for both of these guys. So we have partial xi g multiplied with partial f xi plus g times partial squared f over partial xi squared, so the second derivative, plus again do the same with the f term, plus f partial squared g partial xi j squared. So notice this and this term is the same. So all of this just becomes g times the Laplacian of f, because this is just the Laplacian, plus 2. This is the gradient of g and the gradient of f, but they're dotted together because there's no index on either of them. They have the same index and they're multiplied together. So this is the gradient of f dotted with the gradient of g, plus this last term is just f Laplacian g. So that is what this guy equals. Okay, so now what if we have the divergence of two vector fields crossed with each other, A cross B? Subscript summation convention. Dotted with, I can expand this cross product directly, aj bk epsilon jkl el hat So the Levi-Civita comes out being a scalar, partial xi, and then ajbk Kronecker delta il. We can change this L to an I with the Kronecker delta. So we have jki, which you can shuffle up and write as ijk, partial with respect to xi, ajbk. Now again, use a product rule here. Epsilon ijk partial with respect to xi aj, bk is just outside, plus aj epsilon ijk partial xi, and then we have a bk here. So notice what this becomes. This just becomes the cross, the curl of A. You can check this on a piece of paper if you want, but dotted with B, because there's no basis vector dependency here, because it just got dotted with the B. And also notice that there's a bk, so this k and then this k. So you kind of notice this pattern. And then for this guy here, if we take a negative, we have aj epsilon ikj partial xi bk. I just shuffled the indices of this Levi-Civita. And notice this term, just like the first one, just becomes the curl of B dotted with A. I needed to shuffle because I needed the I and K to match with these indices. So this is precisely what this term turns out to be. Okay, what if we have curl of, say we have two scalar functions, psi and phi, psi gradient phi. So again, subscript summation convention. Crossed with psi partial xj phi ej. Now doing the cross product, we get a Levi-Civita ijk partial xi acting on psi partial xj phi ek. So we get epsilon ijk. Do the cross the product rule again. Partial xi psi partial xj phi ek plus psi partial xi partial xj phi ek. Okay, now notice that this term here is just 0. Why is that? Because we have an epsilon ijk acting on it. So whenever I is equal to j, it's going to become 0 because of the epsilon. Remember that when any two indices of the Levi-Civita are same, it's just 0. So all the non-mixed terms, all the pure terms, so like the terms like del squared over partial x squared, partial squared over partial y squared, partial squared over partial z squared. All these terms are going to become 0. What about the cross terms? Cross terms such as partial x, partial y, partial x, and then their permutations with z. Well, all these terms, they're going to remain, but notice that if you interchange the I and the j, if you like shuffle them, so you just get the same expression but negative epsilon j I k. We just have this, say xi xj so, but this is the same irrespective of any order we put it in. All I'm trying to say, if you shuffle I and j, or you replace I with j, you will get jik, and then the order of these guys switched. Partial xj, xi, ek. But this is like the negative of this guy, right? And these can also be written as xi. You can flip these around using Clairaut's theorem. So all these cross terms are sort of going to cancel each other. So the 1-2 permutation is going to cancel the 2-1 permutation, and you know that holds. So there's a symmetric cancellation going on everywhere for the cross terms, and the non-cross terms are 0, which makes this thing entirely go to 0 because we're summing over all these, even all these symmetric permutations. We're summing over all the permutations, even these symmetric ones. So the symmetric ones annihilate each other anyways. So I hope that argument made sense to you. So this term just goes to 0. So with that, we're just left with this guy here, which is let's see what it is. Epsilon ijk partial xi psi partial xj phi ek. If you notice closely, and again this comes with lots of practice, this is just the gradient of psi crossed with the gradient of phi. So that's what this term turns out to be. It's going to be important, so just let's just mark it as 1. Let me choose another color here. Let's take a red. Let's do number 2. So number 2 is like this. Divergence of a similar quantity, psi gradient phi. So ei partial xi dotted with psi partial xj phi ej hat partial xi psi partial xi. The reason I got xi here again is because we have a canonical delta ij out there. I contracted over the indices and just got this. So again, let's do a chain rule here, a product rule, my bad. Partial xi psi partial xi phi plus phi times partial over xi partial xi phi. This first guy is, if you notice closely, gradient of psi dotted with the gradient of phi plus psi times the Laplacian of phi. That's what this second guy is. And why are they useful? Why have I numbered them 1 and 2? Is because, assuming you're doing closed surface integral, the surface which is a boundary of a volume of psi gradient phi dot dA, this by Gauss's divergence theorem is the volume integral of the divergence of this guy, and the divergence of this guy is exactly number 2 here, that what we calculated. So this just turns out to be psi Laplacian phi plus gradient psi dot gradient phi d tau. This is called Green's identity number 1. And another one is, if you have which is sort of related to the top part, again the surface which is a boundary of a volume of psi gradient phi minus phi gradient psi dot dA. This will just be again the triple volume integral of the divergence of this guy. Notice you just use a similar formula like in number 1, but then you don't have this cross term anymore because both of these those cross terms will annihilate each other. So you just have psi Laplacian phi plus phi Laplacian psi deta. Sorry, there's a minus here, my bad. And this is Green's identity number 2. Okay, what if we have the curl of a cross product? Again, subscript summation. AJBK epsilon JKL EL hat. So we have, let's see, epsilon JKL partial x j AJBK, another epsilon ILM for this external cross product EM hat. So we have 2 epsilons. What we can do is we want to use Levi-Civita identity. So just flip the indices of the second epsilon here. So epsilon JKL, epsilon MIL, such that the last index is the same. And now Levi-Civita identity. I'm sorry, this is supposed to be an I here. Delta Jm delta Ki minus delta Ji delta Km Em hat. So we can contract over the indices here. Partial xi Am Bi minus partial xi AIBM Em hat. And again we can use the product rule, so we get two terms here and two terms here. Bi xi Am plus Am shall xi Bi minus Ai partial xi Bm minus Bm partial xi Ai, but we still have to surround this Em. So this first term, if you notice, the common indices is a special operator. It's the B vector dotted with the del operator multiplied with vector A, because we have Am Em hat, plus now we have A vector, and this time we have the divergence of B minus A dot del B minus B times divergence of A. So yeah, this was a little hard to notice because of this new operator, this dot del operator. But yeah, this is what this turns out to be. Okay, say we have the divergence of curl of a vector field A. Partial xi, the ei hat, dotted with partial xj ak epsilon jkl el hat. We'll do the dot product. We get xi partial xj ak epsilon jkl Kronecker delta il, which now if you contract over the indices, xi xj ak epsilon ijk, because I lose the L, I get an I, shuffle the indices. And again, I think we went over this. You know, there's this, the symmetric terms are sort of anti-commutative, so you get 0. Let's do another one. Let me change my color quick. What if we have curl gradient of some scalar field psi. This now becomes ei partial xi crossed with partial xj psi ej hat. And because of the cross product, we have partial xi, partial xj. Now don't change the order of them, it's important. Psi epsilon ijk ek hat. And again, because of the same argument we used here on top, the symmetric terms cancel off, we get 0. This is all because the partials are symmetric. Like, you can do partial with respect to xi first or last. It doesn't really matter, because we are just assuming that these functions will satisfy Clairaut's theorem, which is a perfectly valid assumption in most cases. At least the cases we'll be concerned with most of the time. Finally, we have a really important one here. Double curl of a vector field. So again, subscript summation. Levi-Civita identity right here. So since these partials are sort of interchangeable, we can use that property. Not quite yet, but soon. Vi minus partial xi Vm em hat. So now you can interchange the partials. Notice we have a partial xi Vi, which will become the divergence of V, and we have a partial xm with the em. So notice that to be the gradient of this, minus, now this is a vector Laplacian. So although we have the same indices for the partials, we have a Vm summing over Em. So this is the expression for double curl of V. Okay, why is this useful? Because if you notice Maxwell's equations, especially this one, curl of B mu naught j 1 over c squared partial E partial t. Now do a double curl on both sides. So mu naught one over c squared partial with respect to t curl of E. Well, this guy, we can use the formula above. Gradient of divergence of the magnetic field minus the vector Laplacian of the magnetic field is equal to, we can assume this term to be 0. We can say there are no sources, that's one of our boundary conditions. 1 over c squared. We can use another Maxwell's equation, so which says the curl of E using Faraday's law is the time derivative of the magnetic field with a negative sign. So we have two time derivatives because one was already out there. The divergence of a magnetic field is 0 by Gauss's law. So this is 0. Drop the negatives on both sides. We have vector Laplacian. The magnetic field is nothing but 1 over c squared, second partial derivative with respect to time, of the magnetic field. And this is your wave equation. Electromagnetism. I just wrote this term as c squared, although in the real version there's a mu naught times epsilon naught in the numerator, which then, because it's in the form of the wave equations, we can deduce that mu naught times epsilon naught is 1 over the speed of the wave squared, which in this case is the speed of light. So you see how useful these things are. Okay, I think this is it for this video. So I can give you one other equation to do in your spare time. The Laplacian of A dot B. You can try doing this. This is Green's third identity. And whatever you get, you can tell me the solution in the comment section. So see you next time, I hope. Please like, share, and subscribe to my channel again. We've reached 500. Thanks again. And in the meantime, stay home, stay safe.